So we're going to start chapter 5 on probability, and that chapter starts on page 203. And in this chapter, we're going to see how we're going to connect something that we learned previously, like, for example, frequency distributions, how these frequency distributions relate to probability. So first, we're going to start with learning about basic concepts of probability. And to do that is just, we're going to read some definitions, and then we're going to try to solve some examples to understand better those definitions. So the first definition is going to be the definition of probabilities. Your book says that the probability of an event is the proportion of times the event occurs in the long run as a probability experiment is repeated over and over again. So this definition is the one that is going to allow us to relate the relative frequency to a probability, because they are talking about the proportion of times the event occurs. So you're going to see later how this relates to a frequency, to a relative frequency. Another definitions that we're going to need to understand. First is the law of large numbers, which says that a probability experiment is repeated again and again. The proportion of times that a given event occurs will approach its probability. So in this, by using this law, we're going to be able to say that the relative frequency approaches the probability of a certain event. So another definition that we need to learn in this chapter is a sample space, which is the sample space contains all the possible outcomes of a probability experiment. And then we have the definition of an event. An event is an outcome or a collection of outcomes from a sample space. Then we have the definition of a probability model. For a probability experiment consisting of a sample space along with the probability for each event. So I just summarized all those definitions for our notes. Oh, actually, I just copied those definitions for our notes. So we have here chapter 5, starting on page 203, then section 5.1, and then the definition that I just read, but that we're going to now try to understand better by solving some examples. So the most important one is the probability of an event. It's the proportion of times that event occurs in a long run. And then the definition of a sample space are all the possible outcomes of a probability experiment. So I'm writing here with a star to highlight the definition of a probability experiment. It's an experiment in which we do not know what any individual outcome will be, but we do know how a long series of repetitions will come out. So in other words, a probability experiment is just an activity. It's a procedure that we're going to repeat a lot of times, and we're going to be able to know at the long run how the distribution of the different events are going to be in our probability experiment. So, and then we have here the definition of an event and the definition of a probability model. So let's start with an example to try to understand this in a better way. So we're going to solve example 5.1, which is on page 205. So I have here page 205. So the example 5.1 is just the following. We're going to describe a sample space for each of the following experiments. So now you're going to see what a probability experiment is. I said it's an activity that you do many times, and you don't know in advance what is going to be the result of those activities. But if you do that an infinite number of times, you might have an idea how the different outcomes are going to be distributed in a frequency matter or frequency table. So for example, the first case is when you toss a coin. So, and then when we roll a die, and the fourth case that we're going to study is selecting a student at random from a list of 10,000 students at a large university. Then we have the last one is selecting a simple random sample of 10 of 100 students from a list of 10,000 students. So let's analyze these cases one by one. So we're going to start first with tossing a coin. So you know that you have a coin and you have heads and you have tails. So what are the possible outcomes? So the possible outcomes is that either you get a head or either you get a tail. So the sample space, then we're going to denote the sample space um, with any name, but we're going to use curly braces to enumerate, to contain, to enumerate the possible outcomes. So one outcome is getting heads, and the other outcome is going to be getting tails. So there are only two outcomes for this sample space, no more. So then when you roll a die, so we have a die, it's a cube with numbers on its faces. So we have 1, 2, 3, 4, 5, and 6. So what are the possible outcomes? You either get 1 up or 2 or any number. So the sample space is a fancy name just for the for the list of the possible outcomes. So the outcomes are just numbers 1, 2, 3, 4, 5, and 6. So there is no a possibility for you to get 7. So, and this is when you understand what a probability experiment is, because you don't know what is going to be the next outcome, but you do know that you're going to have 1/6 of the outcomes are going to be ones, 1/6 of the outcomes are going to be twos, 1/6 of the outcomes are going to be threes, and so on. But you are not going to get a 7, or you're not going to get 8 or 0. So that's a probability experiment. So the sample space then for this probability experiment, rolling a die, are going to be these 6 numbers. Then selecting a student at random from a list of 10,000 students. So you're going to have a list of 10,000 students. So you have a student number 1, and you have a lot of students, and you get a student 10,000. So the first and the last one. So there are 10,000 names here in this list. So what is the sample space? The sample space is just the names of the 10,000 students. So, and you're gonna pick one at random. So you don't know what is gonna be the next student that you're gonna pick. It can be the first one, it can be the third one, it can be the 997th student, but this is gonna be your sample space. Now, we need to be careful with the last problem because it might be confusing. So selecting a simple random sample of 100 students from a list of 10,000 students. So we have a list of 10,000 students. So there are here 10,000 students in this list, but what we're gonna do is we're gonna select a simple random sample of 100 students. So we're gonna create by sampling. Remember, we can use sample, the command sample in R. So you're gonna get a sample of 100 students. So you're gonna have here 100 students selected at random, but you might have another sample where you're gonna have a different 100 students. And you might have another sample with 100 students. Another 100 students that are going to be different from the previous list, and so on. So this is there are going to be a lot of combinations that you're going to have here by playing with this list. So you can use a command in R to find all the possible combinations. The command is choose. You're going to choose 10,000 students in groups of 100 students. If you do this in R, you're going to get a huge number. So let's do that just for you to see how R is going to help us solve this kind of problems. So you have a very huge list of, so we're going to use choose 10,000 students in groups of 100, and we're going to get that number 6.52 0847 times 10 to the 241. So it's like, wow, a huge number of a list of 100 students that you're gonna get by trying to reproduce this experiment. So what is then the sample space? The sample space is gonna be just 6.52 times 10 to the 41 lists of 100 students, and all those lists are going to be different from each other. So that's but yeah, this is just for you to understand the idea of sample space. So you need to read carefully the problem to know what is going to be the answer. So now we're going to try to solve another problems. So I have example 5.2 now. That's the next one. So let's see, we have example 5.2. This example is on page 206. So let's find the example. So we have here page 206. So example 5.2. So example 5.2 says that if fair die is rolled, find the probability that an odd number comes up. So that's the problem. So we have then a die. So if fair die is rolled, and we're going to find the probability that an odd number comes up. So first we need the sample space. So we know that the sample space is just numbers 1, 2, 3, 4, 5, and 6. Now we need a formula for probability. So what is the formula for probability? We need to read the definition one more time. So I'm going to read again the definition. The probability of an event is the proportion of times the event occurs in the long run as a probability experiment is repeated over and over again. So the probability of an event is going to be just the frequency of the event over the total frequency. That's one way to define this. So here, so to have an odd number is going to be just the numbers are 1, 3, and 5. So what is the probability of getting a odd number? Is going to be the frequency of this event. This event only contains 3 elements, and over the total frequency, the total number of events is just 6. So this is going to be 1/2. So that is going to be the probability of getting an odd number when you roll a fair die. So this is important. A fair die means that the probability of getting 1 is the same as the probability of getting 2, and it's the same as the probability of getting 3, and so on. If the die is not fair, then maybe it's a die that they are using in a casino. It might be that the die was manufactured in a way that the number 5 comes up more frequently than the other numbers, but that wouldn't be the case that we will be solving here. So now we're going to solve more problems. We have another example. We're going to solve now example 5.6. Example 5.6 on page 209. So let's see what that example is. So we have here page 209. So we have here this problem. There are 10,000 families in a certain town, and they are categorized by their type of housing as follows. So people owning a house are just, or families owning a house are 4,753. Families owning a condo is just 1,478. Families renting a house, 912. And families renting an apartment, 257. So the questions are, a pollster sampled a single family at random from this population. What is the probability that the sample family owns a house? And what is the probability that the sample family rents? So I'm going to give you just some minutes for you to try to solve this problem just by using the definition that we just mentioned a moment ago, the definition for probability. So we have here our frequency table, our frequency distribution for the families living in a certain town. So we know that some families own a house, some families own a condo, some of them rent a house, and some of them rent an apartment. So, and then someone is conducting some study or survey, and they sample a single family at random from this population. So this is a population. So what, the first question is, what is the probability that the sample family owns a house? So we're going to write the probability that the family owns a house. So the family owns a house. So it's going to be again a fraction. So first we're going to look for the frequency of the event that is our event of interest. In this case, the families owning a house are just 4,753, and the sum of all the frequencies is just 10,000 because we knew that there were 10,000 families in this town. So we're gonna divide this by 10,000. So we're gonna get just 0.4753. So this is the probability. In the second case, now we want to know the probability that the sample family rents. So now we have here that some families rent a house and some families rent an apartment. So to compute the probability of a family that rents only either a house or an apartment. So we're going to combine the frequencies of these two events, so or outcomes. So we have 912 plus 2857. Anytime that you conduct a division and you have several terms in the numerator or in the denominator, please use parentheses to prevent mistakes. So then we're going to divide this by 10,000. So we need to use a calculator or use our console. And remember, we're going to use a parenthesis. Then we're going to write the numerator. So 912 plus 2857, and we're going to divide that by 10,000. So the answer is just 0.33 3769. So that's the probability that if you sample the town, that you're gonna get a family that rents and it doesn't matter whether the family rents a house or an apartment. So that's this problem. So now we're gonna see another definition that we're gonna use to classify events. And this definition is very, very important. We're gonna use the criterion given by this definition a lot of times. So we want to know what an unusual event is. And the definition is very simple. An unusual event is one whose probability is small. So I'm going to write this here in our notes. So let's see. We have on page 209, an unusual event is one whose probability is small. How small, you might ask? So if the probability is less than 0.05, that is going to be the criterion to determine or to decide that that unusual event is that event is unusual. That is a rare event. It's an event that is not common. So let's work now another example. We're going to work example 5.7 from your book on page 209. So this example is about computing another probability, but using that probability to decide whether the event is unusual or not. So in a college of 5,000 students, 150 are math majors, and then a student is selected at random and turns out to be a math major. So is this an unusual event? So to know whether an event is unusual, we need to compute its probability. So that's the first step to solve this problem. So I have here that I want to know the probability of getting a math major student. So, and it's going to be the number of items that favor this event, in other words, the frequency. So the frequency of math majors is 150, and the total frequency is 5,000. So you use your calculator, we use R, and we get 0.03. So that's the probability, 0.03. Then we compare this value with 0.05. So this probability, the probability of getting a math major student, is less than 0.05. So that means that the event of selecting or sampling a math major student is unusual. So it's rare, uncommon event. So that's one of the criteria that we're going to be using later to make decisions when we start working on that on chapter 9. So now I'm going to give you your assignment for this section. It's a lot of problems, but they are very simple in nature. So you're going to see that you can solve these problems very easily. So these problems are on page 213 of your book. So let's see, you're going to solve from section 5.1 exercise set on page 213. You're going to solve first problems 13, 14, 15, 16, 17, and 18. This is just basic. You're going to use just the definition of probability. Then you're going to solve problems 21, 22, 23, 24, 25, and 27. And finally, 40 and 41 to have an idea of what you're going to get in your exam. So try to solve as many as possible. I know that this is a lot of work and you need to take screenshots and get your PDF files. So yeah, but it's not hard. So actually, the first 6 problems is just one problem with a lot of parts, with 6 parts. So we have here. You're gonna need to read that and exercises 13 to 18. Assume that a fair die is rolled, so the sample space is the one that you already know, 1 through 6, and all the outcomes are equally likely. So the die is fair. So you're going to find the probability of getting 2, the probability of getting an even number, or getting a number that is less than 3, or a number that is greater than 2, or the probability of getting 7, or the probability of getting a number that is less than 10. So these are the first 6 problems. So it's like just a single problem. It's not a big problem. So now you're going to solve problems 21 through 27. So it's just the rest of this page. So 21 through 24, you're going to use the sample space that results from tossing 2 coins or tossing 1 coin twice. So it's the same thing. So this is your sample space when you are tossing 2 coins or 1 coin twice. So you might get 2 heads, head and tails, or first tail and then head, or 2 tails. And those are different probability models, and you need to decide whether these are actually probability models, if they follow the rules. So that's problems 21 through 24. So there are some rules that the probability model should follow. So these are the 4 problems. Okay. Then we have problems 25, 26, and 27 here. So 25 is this one. This is just a matching problem. You're going to match a probability and its meaning. So that's problem 25. Then problem 26 and 27. Those problems are here. Then we need problems 40 and 41. So let's see, problem 40 starts here. How many kids? So the General Social Survey asks for 46,349 women how many children they have. And the results are here in this table. So you have a frequency distribution, and then you're going to need to answer some questions about that frequency distribution. And finally, problem 41 is another frequency distribution and questions about that frequency distribution. Just as another note for you, when you are solving the problems related to probability models, you should remember that the probability is always positive, the probability of an event is always greater than 0, greater than or equal to 0, so it's always positive, but it's always less than or equal to 1. So you cannot get negative probabilities or values that are greater than 1. And the other thing for probability models is that the sum of the probabilities of the all events should be equal to 1. So this is something that you need to check when you are working a probability model. That the sum of the probabilities. So if you have your classes, your frequencies or probabilities, your relative frequencies or probabilities, the sum of those frequencies is pretty close to 1. Close. It can be just 0.99 or 1.001 or close because of rounding errors, but that's what you need to solve the problems for this assignment.